Hi, I'm Robert Kollman. I'm a Senior Applications Manager at Texas Instruments. Welcome to Power Tips. Oh, hi, this is Robert Kollman again. In this Power Tip, we're going to take a look at unintended resonant responses in the system. Where you might have an unexpected resonance in your system might be the input to a power supply. For instance, you may have a long cable hooked up your power supply, and that will form this circuit that's shown on the bottom of the slide. We have a voltage source that's connected to our system through a switch, and then we have this resistance and inductance here, and those would represent the resistance and inductance of a cable, or they might represent an intended filter component, where the R is just simply the winding resistance of the inductor. And here you can see what happens to the system as we apply an abrupt voltage step to it. If we have a very high Q system, or that is one where the resistor is quite small, we can see that we can get very severe overvoltage conditions in our systems. We can have overshoots as much as 100% with this voltage step. So that might mean if you had a 48 volt system, you could have a 100 volt peak applied to the system, and that might cause damage in your system that you didn't anticipate. We have seen this kind of problem in power over Ethernet systems where people have used relatively low voltage parts. They'll have a 60 volt part, 55 volt source, they apply the cable, and they damage their circuitry. To control this overshoot, one can just reduce the Q of the system. And one easy way to reduce this Q is just to put the series resistance in and increase it. And you can see that we can control the amount of overshoot by adding this series resistance. So here's a simple method to determine if you have a problem. First thing you have to decide if your system has an abrupt voltage step on the input, and you have to establish that you have a low source impedance. If you have the large resistance we showed in the previous slide, this will not be an issue. Next thing you need to do is estimate the inductance and capacitance in the filter. The inductance in the filter can be estimated either by looking at intended components such as the inductors or using a rule of thumb of 15 nanohenries per inch for wiring. The filter capacitor is simply the input capacitance to the power supply. The next thing you need to do is you need to determine how much resistance you have in the circuit. And that resistance can be the resistance of cabling, it can be the resistance of an inductor, it can be ESR in the capacitor. Once you determine the inductance and filter capacitance in your circuit, you need to calculate the resonant frequency. The resonant frequency is simply 1 over 2 pi times the square root of L over C. And the reason you want to calculate this resonant frequency is to make sure that your input rise time is fast enough to excite this resonance. If you have a slow rising input voltage and a resonance that will not respond to that, you don't have a problem. Also, you want to calculate your damping factor. And here's a simple expression for calculating the damping factor. And the reason that you want to calculate the damping factor is there's a simple chart here that takes you from damping factor to overshoot. So a damping factor 1 is a low Q system, and you get relatively no overshoot. And as the damping factor gets closer and closer to 0 or a high Q system, you see that 100% overshoot that we saw on the first slide. And then by varying the resistance that you've damped with, you're able to control the overshoot. For more power tips, visit the Power Management Design Line webpage and search for Power Tips. Or you can click on the link to all articles in the description section of this video. Thank you.